The next section we're going to look at is a section called Conditional Probability. Now, as the name suggests, when you hear of something that's conditional, well then there's some type of a rule placed over it, maybe some type of a restriction placed over it. And I think the quickest way to explain to you what conditional probability means is that you are reducing the size of the group that you're selecting from. Okay, that's the easiest way to do it. And perhaps the best way to show you that is by a question. In a class, there are 15 male students, 5 of whom wear glasses, and 10 female students, 3 of whom wear glasses. A student is picked at random from this class. What is the probability that the student is female, given that the student wears glasses? Now, there's the word for conditional probability, given. And it also has its own symbol, very similar to the fact that the union of two sets has a U, the intersection has an N, etc. The word given in conditional probability is nothing more than a straight line between the two sets that you're working with. Now notice that there are 15 male students and 10 female students in the class. So that's 25 students altogether. However, there's a further breakdown. 5 of the males wear glasses and 3 of the females wear glasses. So therefore the total number of glasses wearers is 8. All right. Now what are we asked? What is the probability that the student is female given that the student wears glasses? So in other words, you could do it this way. What's the probability that the student is female, straight line between the two, given that the student wears glasses? That's what that straight line means. Okay, well, first of all, if we're given the fact that the student wears glasses, that means we're told to concentrate only on the glasses wearers. So we are not going to be looking at the full 25. In fact, we're going to be looking at the 8 students who all wear glasses. So therefore, the probability we'll be dealing with here will be out of the 8 students who are wearing glasses. Now, what's the probability that the student is female? Well, out of those 8, how many are female? And the answer is, out of the 8 glasses wearers, 3 are female. So there's your answer. And that's conditional probability. So every single time you hear conditional probability, you think of the word given, you think of the straight line, and you know that you're reducing the set out of which you're selecting from, you're reducing the size of that group. Okay, that's the key thing about conditional probability. Okay, so I have the answer there for you also typed out. The sample space reduced to 8, and of these, only 3 girls wear glasses, so the probability is 3/8. So, if A and B are 2 events, now remember I told you about event is just an action, okay? Then the probability of A, given that B has already occurred, is written as P, probability of A given B. So that's the symbolism that we use when we're dealing with this thing. That reads the probability of A given B. Now I've highlighted here in this diagram exactly what that means. The probability of A given B, first of all, it means that we are restricting ourselves just to the set B. So we're looking at this circle B. Okay, now within that circle B, does any belong to A? And yes, it does. There, that does. Okay, this pink region here. So within B, there is an overlap with A. So therefore, in this case, if I was asked what's P, the probability of A given B, I would write down the probability of B as the bottom of my fraction, and I would write down the intersection as the top of my fraction, the same way as the glasses wearers. There was 8 glasses wearers altogether, but only 3 of those were female. Okay, that was the intersection between females and glasses. So there is a formula, and the formula is coming up here now. If you're asked to get the probability of A given B, all you do is you write down their intersection over the second group. So the probability of their intersection over the probability of the second group. So in this case here, take a look at that fraction. A given B, what does that mean? Focus on the probability of B, there it is, as your denominator, and then look within that circle for any intersection with A, and there it is. So just say, for example, if that was 3 and this was 7, okay, well then the answer to this up here would be 3/10, for the very simple reason that the probability of A given B, focus on B, that would be 10. What's the intersection between A and B? 3. Now that's if they were giving you numbers. Obviously there's no numbers in this one, I've just put them in. So that's the formula, okay? Since that the sample space has been reduced to B, the probability of A given B is simply calculated against it. Now that's the English for the formula, but it's the formula that I want you to remember. That's extremely important. So I hope you're making notes as we go through these slides as well, will be important. Okay. Conditional probability reduces the size of the sample space. Now, here's another example. A couple have 3 children. find the probability that all 3 are girls given that at least 1 is a girl. Now you see that given? That reduces down the size of the group we're going to be dealing with. So, for example, it doesn't just say a couple has 3 children, find the probability that all 3 are girls. It reduces it down to those sets of 3 children where at least 1 is a girl. Now I have this typed out for you. So what's the sample space? Well, there could be 3 girls. There could be a boy with 2 girls. There could be a girl, a boy, and a girl, so they could alternate. Because don't forget, this is a permutation. The order is important. Yeah, babies are born one after the other if they're born singly, so the order is important. You might have 2 girls first followed by a boy. You might have a girl followed by 2 boys. You might have a boy, girl, boy, or you might have 2 boys followed by a girl. So at least one of those is a girl. So there's the sample space that you're pulling from. So you've reduced it down to just this number. Now, is there anything in common between 3 girls in that set? Yeah, it's there once. So therefore, out of 1, 2, 3, 4, 5, 6, out of 7 possibilities, one of those represents the 3 girls. Okay, and that's it. That's how you do your conditional probability. Okay, so only one of the above outcomes fits the demands of the question. So therefore, the probability of having 3 girls, given the fact that there's at least 1 girl, is 1 over 7. Okay, let's take a look at this. Given the Venn diagram as shown, find number 1, the probability of x given y, and number 2, the probability of y given x. Now, this is typed out, but I'm going to go through it with you first, and I'll take off the writing in a moment. Okay, take a look at this. The probability of x given y. So straight away, there's y. Okay, so therefore, the total inside y is 0.3. Out of that, the intersecting part of y with x is 0.2. So therefore, the answer to that is 2/3. Okay, what about the probability of y given x? Well, in that case, we're now dealing with this one here, which again, you add in the 2 because it's all that circle is 0.5, and the overlap between y and x is 0.2, which would be 2 over 5. So therefore, we can't say they're the same either way around. They won't be. The probability of y given x is not the same as the probability of x given y, all right? Because they're 2 very different answers here. So you could use the formula as well. Your sample space is reduced to y equals 0.3, and from this we've got x being equal to 0.2, as I went through a moment ago with you. So you put the intersection over the total in y, and that becomes 2/3. For the second one, we are down to 0.5. That's your sample space is reduced down to that, and out of that 0.5, only 0.2 belongs to x, the overlap, so that's 0.2 over 5, which is 2 over 5. That's it. So it's clear to see that they are not commutative, okay? So they don't do the same thing forwards and backwards, and that's extremely important. Okay, another example. Now we'll take some examples from the book. In a class of 25 students, 14 play Gaelic football, 10 play hurling, 7 play neither Gaelic nor hurling. Now in a situation like that, doesn't that bring you back to junior cert with the Venn diagrams? Use them. So draw a Venn diagram. Let's have a look. What does this look like? Well, 25 students, so the universal set is equal to 25. Okay, 14 play Gaelic football, and then the others play hurling. So Gaelic and hurling. Now, 14 play Gaelic, 10 play hurling, and 7 play neither. So the 7 that are out here, they're easy to put in. And now we've got to fill in these. No mention of an intersection. However, if you add up the 14, the 10, and the 7, that gives you 24 and 7, which is 31. But there's not 31 people in the class, there's only 25. So therefore, if you take away the 25 from that, that gives you the intersection of 6. And we've had that already when we were dealing with junior cert stuff. Okay, so that's 6. Now, go back again. 14 play Gaelic, so that must be 8 more in there to bring the Gaelic to 14, and then 10 play hurling, which must be 4 more. Now if you add those up, that should give you the full class. So that's 10, and those 2 are 15, so 10 and 15 is 25. So at least you know that you have your Venn diagram worked out correctly. How many play both Gaelic and hurling? See that lovely N in there? N means intersection, so therefore the answer is 6. And then what is the probability that a student plays Gaelic given that the student plays hurling? Now, what's the probability that a student plays Gaelic given that they play hurling? What does that mean? That means that we've got the probability of Gaelic intersection hurling over the probability of hurling. That's it. That's the formula, okay? Much easier to do in practice. What does the given mean? We're going to restrict ourselves just to H. So we're restricting ourselves to 10. And out of those 10, those who play Gaelic are 6. So the answer is 3/5. Okay, next question. In a certain country, 70% of the population live in a townland and 30% live in a rural area. 50% of the townlanders listen to the local radio, whereas only 20% of rural dwellers listen to the local radio station. A person from the county is picked at random. Find the probability that this person is a townlander, given that the person listens to the local radio station. Now, you can do this in one of two ways. Because there are two different descriptors. You've got rural and you've got townlanders. Then you have people who listen to the radio, local radio, and those who don't listen to the local radio. So I'm going to introduce something here which I'm going to talk about later on. They are called tree diagrams, and you've done these before, I'm sure, for your junior cert. So let's just start here. So there's your population. What are we told? We're told that the population itself is broken into two groups. We're told 70% live in the townland, that's percent. So 70% live in the townland and 30% live in the rural area. Okay, now keep in mind, and I think you might have done this for your junior cert as well, the arms always have to add to 100% or to 1. Okay, just keep in mind also that 70% is better known as 0.7. So I'm just going to do that and that here. I'm going to turn them into their proper mathematical form. So that's 0.7 and this one here is 0.3. Okay, what about them? 50% of the townlanders, so we're up here, so they're further broken down into 0.5. So 50% of the townlanders listen to the local radio. So that means the other half must be listening to some other radio station. Okay, whereas down on the rural side, what are we told? Only 20% of rural dwellers listen to the local radio. So 0.2 and then 0.8 listen to the other radio. Question. Person from the county is picked at random. Find the probability that this person is a townlander, given that the person listens to local radio. So probability that the person is a townlander, given that they listen to local radio. What does it mean? It means the probability of being a townlander and listening to the local radio over the probability of listening to the local radio. That's what the formula tells us. Now we can get all that from here. So what we normally do with tree diagrams is we multiply out the arms. So townlander who listens to local radio, 0.7 by 0.5, 0.35. A townlander who listens to the other radio stations, 0.7 by 0.5 is 0.35 again. A rural area dweller listening to local radio, 0.06. And a rural area person listening to other radio, 0.24. And I hope you notice, if you add all of those up, what do you get? 1. Why? Because that's the biggest probability we can ever have. Can't go over 1. So they should all add up to 1. Now, let's go up here. So the fraction is the probability of a townlander and local radio. Townlander, local radio. So 0.35 goes on top of my fraction. And the probability of local radio. Well, hold on a sec. That's a local radio. And that's local radio. So you add both of those together. That's the total probability of local radio. And that will give me 0.41. Which gives me 35/41. That's it. Okay, now I'm introducing a tree diagram here because I want you to cast your minds back to how they work so that when I do them later on, there won't be any big mystery to you. E and F are two events such that P of E, that's the probability of event E, is 2/5. The probability of F is 1/2. And the probability of E given F is 1/9. Find the probability of the intersection of E and F, find the probability of F given E, and find the probability of E union F. Now let's start at the beginning. So first of all, we have this thing here. Yeah, keep in mind that has a formula. P of E given F is equal to the probability of E intersection F over the probability of F. So in other words, we are reduced down to F, and above that we're looking at the intersection between these two. Now what are we told that's equal to? We're told that that's equal to 1/9. So what's the intersection? Well, that's what we're being asked for, so let's call that X. Over, what's the P of F? Well, P of F is here, it's a half. So what do? If we're dividing over here by a half, we will multiply over here by a half. So a half times a ninth is equal to x, which is 1 over 18. And that's P of E. Sorry, that's the value of x, isn't it? That's, yeah, so that's the value of x. That's P of E intersection F. Okay. Second one, the probability of F given E. Now in this case, that's the probability of F intersection E over the probability this time of E. So we reduce down to E and we're looking for the intersection between these two. The intersection of F and E is the same as the intersection of E and F. That's 1 over 18, which we found already. And that's over the probability of E, which is up here, as 2 over 5, which is 1 over 18 multiplied by 5 over 2, which is 5 over 36. Okay. And the last one then, the probability of E union F. Well, what does that mean? We've got to ask ourselves, first of all, what does union mean? Union means E or F. Think. If we're using the OR word, we're using the addition function. But there are two versions, depending on whether E and F are mutually exclusive or non-mutually exclusive. If they are mutually exclusive, they will have no intersection. If they are non-mutually exclusive, they will have an intersection. Guess what? They have an intersection. Here, we tested it out earlier on. They do have an intersection. So therefore, that means that when we're using the union formula here, we've got to do the following. It's P of E plus P of F, and because they are not mutually exclusive, you take away the intersection between the two. So P of E is 2 over 5, P of F is 1 over 2, and then you're going to take away the 1 over 18. And again, just to do that on your calculators, using the fraction button, 2 over 5 plus 1 over 2 minus 1 over 18 comes out as 38 over 45. And that's it. So you still have to remember what we were doing in previous sections, and particularly for this thing here, because there are two versions of the formula depending on whether E and F are mutually exclusive or non-mutually exclusive. Don't forget that. If they're mutually exclusive, you just add them because they don't have any overlaps. You just add them together. If they're non-mutually exclusive, if they have an intersection, then you have to add them together and take away the intersection to prevent the overlap being counted twice. And we had that before. Okay, in a certain school, 27% of students got an A in junior cert maths, 15% got an A in science, and 9% got an A in both. A student is selected at random, and then they want you to find a probability, blah, blah, blah. Now, let's think about that. A student in a certain school, a student got an A in junior cert maths. So an A in maths was equal to 0.27. Okay. An A in science was equal to 0.15. And then we're told an A in maths and, see that? Intersection again, the N. Maths and an A in science. And that was equal to 0.09, which is 9%. Again, best thing to do here, let's take a look at a Venn diagram. Maths, science. Okay, it's an A in maths and it's an A in science. Okay, so what are we told? First of all, those who got an A in maths and an A in science, 0.09, that goes in here, because you always begin these things at the intersection. Now, how many got an A in maths? 0.27. So therefore that leaves 0.18 in there to bring it up to 0.27. And an A in science was 0.15, so that's going to be 0.06. So if we add up, just to make sure, we're supposed to have, this is supposed to add up to 1, because the universal set for the probability in this case here is going to be 1. So 0.18 plus 0.09 plus 0.06 comes out as 33 over 100, 0.33, which gives me 0.67 out there that didn't get an A in science or maths. Now, we have our Venn diagram. Everything on the Venn diagram is going to help us answer the questions. Part 1. Find a probability that this student got an A in maths given that they got an A in science. So an A in maths given that they got an A in science. That's the probability, the first one you want to work out. So what do we do there? Use the formula. The probability of A in maths intersection A in science over the probability of an A in science. So that's what we're dealing with. So what's that? 0.09 over an A in science is 0.15. So therefore the answer is 9 over 15. Okay, because you can bring your fraction from 0.09 over 0.15 to 9 over 15. Okay, the next one. This student got an A in science given that she got an A in maths. So the probability of an A in science given that she got an A in maths. What does that give me? Now again, we're dealing with an A in maths first of all. So an A in maths is 0.27, and then the overlap with science is 0.09, which is 9 over 27, which is 1 over 3. Okay, part 3. This student got an A in maths or science. Now be careful, an A in maths or science. Or means that we're going to add. So therefore, or means add, but it also means the union of the two sets. So this one here is the probability of an A in maths or an A in science. And we can do that straight away because there's the union. Everything in there is the union. So you've got 0.18 plus 0.09 plus 0.06, which is 0.33 over 0.33. That's it. 0.33 over 1. Yeah, which is 0.33. That's it. Just add them together. That's all you've got to do. Add the 3 boxes there because that's A in maths, union A in science. And the last part, this student got an A in neither maths nor science. So the only people who didn't get an A in maths and science are those who are out here. So therefore, those who didn't get an A, which would be P, A, maths, nor in science, union, A of S, complement. Remember that? Everything outside is 0.67. So they're the people who got an A in maths or science. The people then who didn't get an A in maths and science are outside the union. So you call it A in maths, union A in science, complement, which means outside those groups. Okay. Now, I'm going to let you work away on these. Go to page 70 and 71 of your books. You work on those questions. And again, will you email me if you have any difficulties with them? Okay, so we'll move on. Hopefully those questions were doable. And again, the conditional probability is a lovely thing to be able to use because it reduces your sample space and also because of the fact that there's a nice formula behind it. So I want to just move a little bit more forward now and take a look at probability again when 2 events are happening, but one after the other. And there are 2 possibilities here. Okay, first of all, you think of yourself as holding a pack of cards. If you were to select 2 cards, there are 2 things you can do. You can select a card, like they do in the magic tricks, take a card, have a look at it, don't tell me what it is, and put it back in. So out of 52, you choose 1, you put it back in, which means you have restored the group back to 52. Okay. The other thing sometimes people do is they take a card and they keep it, which means that future probabilities are out of 51. And if you were to take another card, the future probability would be out of 50. So therefore, we've got 2 things that can happen. If you would have an event one after the other, you've got to be careful. Are we replacing the previous event or are we keeping it out of the original group? And if it's being kept out, then that means you're going to change the denominator of the fraction representing the probability by 1 for each successive thing that you actually remove. Okay, so if 2 events happen one after the other, then the probability that the first event happens followed by the second event is given by the probability of E1 intersection E2 is the probability of E1 multiplied by the probability of E2 given E1. Now again, this will make sense when we do the questions. So if I draw 2 cards from a full pack without replacement, what is the probability that I draw a king followed by a queen? Now we're doing it without, I've underlined without replacement for a reason, because that means that first of all, if I draw a king, let's just work out the probability. It's going to be a probability of a king. So that's going to be 4 out of 52. So that's the P of the king. Okay. What about the probability of a queen? Now be careful. The probability of a queen is 4 out of 51 because we're told that we don't replace the card. So that means there will be 4 out of 51. So what's the probability that I draw a king and a queen? Which means we're going to multiply these 2 together. So that's what this thing up here actually means. All right. It means that you do the first probability as normal. then you make any adjustments required to the next probability if you keep the object out, if you don't replace it. So in that case here, we get 4 over 52 multiplied by 4 over 51. And that comes out as 6 over 663. Whoops, I'm wrong. I'm not reading that right. My glasses, I need new ones. It's 4 over 663. So that's the probability if I take a king, leave him out there, and then go back to the 51 to select a queen. So full pack, 52, 4 kings. If I take a king and leave him out, there's 51, but there's still 4 queens in there. So you can actually hear the fractions if you think about these things logically. Okay, that's there for you to have a look at. Let me just remove my own scribbles and annotations so you can see it. Okay. Now, 3 cards are chosen at random from standard pack. Find the probability that all 3 are kings. So you're taking 3 cards, 1, 2 and 3. You're not replacing them because you're taking 3 cards out of the pack. So there's no replacement here. First of all, we want P of a king and the probability of another king and the probability of another king. So in that case, that'll be multiplication, that'll be multiplication. Now, what's the probability of the first king? Well, there are 4 kings out of the full pack. Put them aside, that leaves 3 out of the 51, which will leave 2 out of the 50. Okay, so in a situation like that, and again, these just take a little bit of time when you're doing the multiplication with your fractions, 4 over 52 multiplied by 3 over 51 multiplied by 2 over 50. And the answer there comes out as 1 over 5,525. So very, very slim chance. Okay, that's part 1. Part 2. What is the probability that none of the 3 cards is a king? Okay, so therefore the 4 kings are out of the question. Doesn't that drop me down to 48 cards? So the first one can be any of the remaining 48 out of the 52, but I'm going to hold that, which gives me 47 out of the 51, which then gives me 46 out of 50. Okay, and again, do the 3 fractions. So 48 over 52 multiplied by 47 over 51 multiplied by 46 over 50. And that comes out as 4,324 over 5,525. Another way to explain that, a very high probability. Okay, part 3. At least one is a king. Now, when you hear these questions, at least one is a king, I'm going to give you another way to think about these, because at least one of a king means you could have 1 king and 2 non-kings, or you could have 2 kings and 1 non-king, or you could have 3 kings. Okay, but there's another way to do that. Think about that. It can be 1 king or 2 non-kings with 2 non-kings. It can be 2 kings with 1 non-king, or 3 kings. There's only one option left out there. What can it not be? It can't be no kings. All right, so therefore in that case it's going to be the opposite to this. So instead of saying at least 1 king, I'm going to say 1 minus the probability of no kings. See that? So it's kind of thinking the same statement in the other way. So at least 1 king could be 1 king or 2 kings or 3 kings. But therefore those 3 options are also best described as the option that doesn't have any kings. So that's the opposite way of looking at this thing. So that's an easier thing to do here. So it's going to be 1 minus the probability of no kings, which we've just worked out a moment ago, was 4,324 over 5,525. So 1 minus the answer comes out as 1,201 over 5,525. And then the last part, part 4. Now, exactly 2 are spades. So how many times could I get that? Well, I could get what? I could get a spade, and a non-spade. I could get a spade, a non-spade, and a spade. Or I might get a non-spade with 2 spades. Okay? So in other words, there are 3 permutations for this particular question. So what I would suggest you do is you just work out the first one and multiply it by 3, because there are 3 arrangements, 3 different arrangements of the same result. Now that's important. So let's just work out this one first of all. Spade. What's a spade? A suit. How many cards in a suit? 13 over the 52. I want another spade, 12 out of 51. And now I want a non-spade. Well, if the 13 spades are gone out of 52, doesn't that leave 39 out of the remaining 50? I hope you can see that. Okay, so multiply those out. So we get 13 over 52 multiplied by 12 over 51 multiplied by 39 over 50. And that answer there comes out as 39 over 850. Now that's just the answer for this part. But there are 3 different arrangements of the same result. So we multiply that by 3. And when we multiply that by 3, we get an answer of 117 over 850. And that is the probability that exactly 2 of those cards are spades. Jim, Ken and Leah are given a maths problem to solve. Their probabilities of success are shown in this table. Okay, so Jim, Ken and Leah. They have success, but don't forget they'll also have failure. Jim's success is a half, so his failure must be a half. Ken has a success of a quarter, poor Ken, and his success or his failure rate must be 3/4. Leah has a success rate of a third, so her failure rate must be 2/3. Do you always see the way sometimes there's extra information hidden behind the information that's given? So make sure you get your table out like that so that every eventuality is ready to go. Find the probability that all 3 are successful. So I want Jim to be successful and Ken and Leah. 1 multiplied by 2 multiplied by 3. So in that case, we take a half, we multiply it by a quarter, and we multiply it by a third. Okay, and that's going to give me 1 over 3/4 or 12 times 2 is 24. What about all 3 fail? Well, if all 3 fail, that's going to be a half by 3/4 by 2/3, which will be, and look for cancellation always when you're doing these things, quarter. Okay, because sometimes that's so easy to get when you cancel things. And lastly then, at least 1 is successful. In other words, nobody fails. Okay, so nobody fails. So instead of saying, well, there could be 1 successful or 2 successful or 3 successful, the opposite to at least 1 successful is nobody fails. So that's going to be 1 minus what? Nobody fails. 1 minus the fails. So if nobody fails, that's going to be 3/4. That's it. Now again, you can use all 3 are successful. You should use the notation maybe, you know, P of S times P of S times P of S and so on. But you can do that as you wish yourself. That'd be P of F by P of F by P of F. And then this one down here would be 1 minus the probability of failure. So if you're not allowed to have anybody fail, then take out the failures from 1, and that leaves you with the probability that at least 1 is successful. Okay, so I hope you're staying with me. Independent events. Now, these are events where the action of the first event has no influence over the probability of the second one. Okay, so therefore, when you do the first event, the probability of the second one is left unchanged. And a typical example of that would be tossing a coin and then rolling a die. Okay, so if you toss a coin and you roll a die, what does that mean? Does the coin influence the die? No, absolutely not. So these are independent results. So we say that A and B are said to be independent if the occurrence or the non-occurrence of the first event does not influence the probability of the other occurring. So in other words, if there's no overlap, then one can't affect the other. If there's overlap, maybe they can, but in this case, they can't. So if you're taking a card from a pack and then you're going back to the same pack, well, then you're going to influence the probability of future events if you take the card and leave it out. Here, if you toss a coin and you throw a die, the coin can't influence the die, no more than the planets can influence our star signs, but the coins can't influence the die, so therefore they would be called independent events. And A and B are independent whenever 3 rules are met. Okay. Now, the lovely thing about this is you only have to choose one and stick with it. I would suggest a third one, but let's go through all the rules first of all. So A and B are independent whenever the probability of A remains itself even though you're given B, or the probability of B remains the same even if you're given A. So in this case here, The probability of A given B, so even though we're told focus on B, it doesn't have any effect on A. The probability of A is left unchanged. But if we're told to focus on A, and the probability of B is unchanged, then they're independent, okay? The outcome of one event, as I told you already, has no impact on the outcome of the other. And if that's the case, you just follow the old rule. If you're dealing with event A and event B, think of the end of the word and, it's the intersection, and intersection means multiply. There are three conditions, as I told you already. Now, I would ask you to look at the last one. The last one's the easiest enough one to remember. If somebody said to you, are these two events independent? Well, then all you've got to do is work out their independent, work out their individual probabilities, multiply them, and the answer should be the same as their intersection. All right? I think that's probably by far the best one to remember and the best one to utilize. Okay. Any one of the three can be used to test for this independence, but I would ask you maybe think of the third one because it's an awful lot more intuitive. Example, 4 people are asked on what day of the week they were born. Find correct to 2 decimal places the probability that at least 2 of them were born the same day of the week. Now here we go again, at least 2 of them. What does that mean? 2 of them on the same day, 3 of them on the same day, 4 of them on the same day. What's left out? What's not allowed? What's not allowed is that they were all born on different days. So therefore, if I want to find out the probability that at least 2 of them were born on the same day, why not take 1 and remove from that the probability of different days? That's the easiest way to do it. So always take the opposite statement to the one that's given. When you hear those words, at least, yeah, they tell you to look at the opposite statement and take that away from 1. So 4 people, 1, 2, 3 and 4. What about them? I want to see in how many different ways could they be born. What's the probability of being born on different ways? Well, take person 1. Person 1 out of the 7 days can be born on any of the 7. Person 2, to be different, can be born on any of the remaining 6 out of 7 days. Person 3 on any of the remaining 5 out of 7. And person 4 on any of the remaining 4 out of 7. So in a situation like that, if I want to work out what's the probability of all different days, then I simply multiply these. And you don't have to bother with the first one because that's 1, so don't worry about that. So what do we get? 6 over 7 multiplied by 5 over 7 multiplied by 4 over 7. And that comes out as 120 over 343. Now that's the probability of being born on different days, but I want the opposite of that. I want at least 2 of them born on the same day. So it's 1 minus 120 over 343. So 1 minus the answer, and that comes out as 223 out of 343. And that's the probability that at least 2 of them were born on the same day of the week. And we had that one already. That's Jim, Ken and Leah. There's a surprise. Okay, so let's work on to this one. If P of A, the probability of A is 0.4, probability of B is 0.3, and the probability of A union B complement is 0.42, prove that A and B are independent. Okay, well let's take a look first of all. What does the Venn diagram look like? There's A, there's B. Now where do we begin? Well, let's begin outside with the A union B complement because that's the only thing we do know. We also know that 0.4, 0.3 and 0.42, they're way over 1. You can't have over 1 in probability. 0.4 and 0.3 is 0.7. 0.7 and 0.42 is 1.12. So therefore that means that 0.12 must be in the middle. Okay. Now, if 0.12 is the intersection, then that's going to bring A down from 0.4 to 0.28. It's going to bring B down from 0.12 to 0.18. And now we've got everything we need. So now what are we asked? Prove that they're independent. If they are independent, so if independent, then what? Then their individual probabilities, A and the probability of B, when multiplied, should be equal to the probability of their intersections. That's what independence means. So let's do that. What's the probability of A? The probability of A is 0.4. So 0.4. What's the probability of B? Add those two together, you get 0.3. When I multiply those together, I get 0.12. Is 0.12 the intersection? Yes, it is. Are they independent? Yes, they are. Okay, we've done that. A green six-sided die and a red six-sided die are rolled. E is the event that the score on the green die is 1, and F is the event that the total on the 2 dice is 7. So investigate if E and F are independent. Now again, if E and F are independent, write down what it means. The probability of E multiplied by the probability of F should be the same as the probability of E intersection F. And that's what we need to look at. So the probability of E, what does it say? E is the event that the score on the green die is 1. So how many ones on a die? There's only 1 out of 6 numbers. So that's the 1 out of 6. F is the event that the total on the 2 dice is 7. So if I'm only allowed to have 1 on the first die, that means I can only have 6 on the other die to bring it up to 7. How many 6s on a die? 1. So 1 out of 6 is the probability of F. So what we need to then ask ourselves is this. Is there an intersection? Well, let's multiply it. 1 over 36. E intersection F means you multiply the 2. And let's think about the sample space. Let's just think about this for a moment. There's 1 to 6. 1, 2, 3, 4, 5 and 6 of the first die. And there's 1, 2, 3, 4, 5 and 6 of the second die. If you were to fill in all those grids, there would be 36 possible outcomes. Yeah. One of those 36 is 1, 6, which is here. There's 1, 6. So if you were to fill out all that grid with all the different couples, you get 36 couplets, yeah? So 36 would be the total. And out of those, only one of them can give me the 7 if the green die is 1. So therefore, the intersection of the 2 is 36. So if I multiply 1 over 6 by 1 over 6, I get 1 over 36. And from this table here, it's clear to see that out of the 36 possible outcomes, only one of them can give me a green die with 1 and a second die with 6 to bring the total to 7. So therefore, yes, their product is the same as their intersection, and if that's the case, they are independent. Now, we've talked about these already. These are our tree diagrams, and these are very handy things to use because they allow us to see how the event 1 shapes the probability of event 2. Okay, so this is the whole idea behind this section. How does one event shape the outcome of the second event, and so on. So just to take an example here, a box contains 4 blue spheres and 2 yellow spheres. 2 spheres are drawn at random from the box. What is the probability that one sphere is blue and the other one is yellow? Now, we've got 2 ways to do this. What's the probability that one sphere is blue and the other is yellow? Let's just write down what are the 2 possible outcomes. Blue, yellow, and yellow, blue. Okay, they're the 2 outcomes. Blue and yellow, or yellow and blue, because it doesn't say about the order. It's a combination, not a permutation. So it just says what's the probability that one sphere is blue and the other is yellow. It doesn't matter about the order. So you can have blue and yellow, or you can have yellow and blue. So both of those must be taken into consideration. Now, how many blue spheres are there? Well, there are 4 and 2. So there are 6 altogether. Okay, 4 of them is blue, and out of the 6, 2 of them are yellow. So we just make a note of those 2 because they're the probabilities that we're going to use. However, if we take 1, it says here that 2 spheres are drawn at random. So you take out the first one, hold on to it, and take out the second one. So blue and yellow. 4 out of 6 represents blue, but because I'm going to keep that out, we drop down to the available number of spheres, which is 5. And out of that 5, 2 of them will be yellow. So I want a blue and a yellow, which is 4 over 6 multiplied by 2 over 5. What about yellow and blue? Well, go back to the bag again. There are 6 in there. Of those, 2 are yellow. So that's 2 out of 6. And if I take out one yellow one, that drops the number of spheres to 5. And 4 of them are going to be blue. So it'll be 2 over 6 times 4 over 5. And when we work those out, we get 8 over 15. That's it. So that's how you do it if you're going to logically write it down. How does the tree diagram work? Well, it works like this. Here are your spheres. Okay, so that's all your spheres together. We're told here that 4 out of the 6 are blue and 2 out of the 6 are yellow. Remember I told you the arms always have to add to 1. Yeah. Here we're then told if I select a blue one, well then 3 of the remaining 5 are still blue and 2 of the remaining 5 are yellow. However, if I select a yellow, well, what does that mean? That means that 4 out of the remaining 5 are blue, or only 1 out of the remaining 5 are yellow. So you can break your arms up that way. And then with tree diagrams, what do? We take the arms and multiply them. So we want a yellow or blue, or a blue and yellow. So there's the first one. Blue followed by yellow, or a yellow followed by blue. So therefore we take these two together. 4 over 6 multiplied by 2 over 5, there it is there. And then we take these two together, 2 over 6 multiplied by 4 over 5. We add them together and we still get 8 over 15. So therefore the tree diagram for some people is an awful lot easier in order to spread out all the possibilities and see how one event then interferes with the second event after that. Or you may go back to the previous slide, you may just write it down as simply as being logical and work it out in your head. Either way is perfectly fine. Okay, so if a day is fine, the probability that Mary will be late for school is 0.4. If the day is wet, the probability goes up to 0.5. In Ireland, 20% of all school days are wet. Okay, so here's two types of days. First of all, you've got a fine day and you've got a wet day. Now, in Ireland, 20% is wet, so that's 0.2, so that must be 0.8 because the arms have to add to 1. Okay, let's see what happens on a fine day for poor Mary. On a fine day, where is it? If the day is fine, the probability that she'll be late is 0.4. So now we've got late and we've got early. So 0.4 that she's going to be late, meaning 0.6 she's going to be early. But if the day is wet, this goes to 0.5 each, because 0.5 and 0.5 make 1. So there's late and early. Okay, so that's how you would do the tree diagram for that. Okay, what does the question ask? Let's just get rid of that. The question says the following. Find, using a tree diagram, the probability that on a random school day in Ireland, Mary will be late for school. Okay, so there's your diagram as I drew it a moment ago. Now, what is the probability that she will be late for school? So therefore, we take this one and we take this one. So we're going to take this arm, late, and we're going to take this arm here, which is late, straight down that way. So 0.8 by 0.4 is 0.32. There it is there. And then we have 0.2 by 0.5, which is 0.1. So therefore we get 4 eighths are 32. So 0.32, all right. And then here 0.5 by 0.2, 0.01. Don't know where that came from. So that's 0.32. 0.2 by 0.5 is 0.01. Right now, 5 2s. Yeah, 0.01. So that will give me 0.33 as our answer. I hope I'm okay with that. That's correct. So 0.8 by 0.4 is 0.32. 0.2 by 0.5. If that was it'd be 1, so 0.1. 0.1 I should say. 0.1. Yeah. So 0.2 by 0.5 is 0.1. Sorry, 0.1. So that gives me 0.41. That's it. Or 0.42. Actually, I've got the 2 is up there. So 32. So 0.42 is the answer to that one. So again, the arms will help you to work that one out. Okay, I think we're coming towards the end of this now, so bear with me. Work the example, page 82, question 11. Prove that E and F are independent events. This is very simple. If two events are independent, it means that the probability of E multiplied by the probability of F is equal to the probability of, as we said, or equals the probability of E intersection F. That's independence. So let's see. Probability of E. Well, take these two together. That's E. So add these two fractions together. That's 3 over 15 and 2 over 15. So that's 5 over 15. Multiplied by the probability of F, which is 6 over 15. Now, if I multiply those together, just bear with me. So multiply 5 over 15, which is a third. So do your cancellation. And then that goes in there 2 times. That's going to give me 2 over 15. And check. Is that the same as what's inside the intersection? Yes, it is. Are they independent? Yes, they are. E and F are independent events whose cardinal numbers are given in the Venn diagram. Find the value of X. And then it says you may assume that all single elements are equally likely. Now again, the key word in this question is independent. P of E multiplied by P of F must be equal to P of E intersection F. That's the rule for independence. Okay, Now, P of E. Well, what's P of E? Let's take a look and see. P of E, what's the total in the whole universal set? Well, first of all, the universal set is 9 and 6, which is 15, and 30, which is 45, and x. So we have to write this down as 45 plus x. Now, 45 plus x is the universal set. That's going to be the denominator in all of our fractions. The probability of E, therefore, is 15 out of 45 plus x. That's going to be multiplied by the probability of F, which is 6 plus x over 45 plus x, good. And that's equal to the intersection, which is 6 over 45 plus x. Now, just allow me to simplify this. That and that will cancel. So you're dividing here by 45 plus x. You're dividing here by 45 plus x. So you can knock one of the denominators out on both sides. And what that's going to leave me with is, that's going to leave me with 90 plus 15x over 45 plus x is equal to 6. And you notice that I have one variable. I can solve this. So all I've got to do now is to multiply across by 45 plus x to clear the fraction. 90 plus 15x equals 6 5s are 30, 24, that's 270 plus 6x. 15 minus 6 is 9x equals 270 minus 90 is 180. So x must be 2. So we go here and we put our 2 in. Okay, so that's it, done, finished. And let's just make sure that that is the case then. If we were to do this properly, we'd have 15 over 47 multiplied by 8 over 47, and that should be equal to 6 over 47, and you can check that yourselves. There are 20 raffle tickets in a hat numbered 1 to 20. 4 of the tickets, numbers 5, 10, 15 and 20, are green, and the rest are pink. Okay, so let's just start making this. 4 of the tickets, 5, 10, 15 and 20, are green. So 5, 10, 15 and 20. So they're the green ones. And then pink is the rest. Okay. A ticket is picked at random from the hat and then placed in the hat. So it's replaced. That's important, because then by replacing that particular ticket, it doesn't affect the outcomes of the ones afterwards. The denominator that will make up our probability fraction will remain the same. Once more, then, a ticket is picked from the hat. E is the event that the first ticket is pink. So E equals pink. And F is the event that the total on the two numbers is 35 or more. So F is the event that the total is greater or equal to 35. Okay, number 1. Without listing them, state the number of elements in the outcome space S for picking 2 tickets. Okay, how many tickets are available to pick the first time round? 20. What do you do after you pick your ticket? You put it back in again. So how many are available again for your second selection? 20. So I want ticket 1 and I want ticket 2, which means that there are 400 elements in this, what we call sample space. This is all the results, all the outcomes. Okay, part 2. Find P of E. Now, P of E, pink tickets. So the P of E is just the pink tickets out of the whole lot. And that is obviously, how many of them are pink? Pink is what? Pink is the rest of these. So you take the 4 of these green ones away, and that gives me 16 over 20, which will be the same as 4 over 5. Find P of F. Okay, well, P of F in this case is the total greater than or equal to 35. Now we're going to have to think about this one, okay? If we were to pick 15, then we would have to get a 20 in the second draw. So there's your first draw, there's your second draw. Let's just think about this. Then if I was to pick 16, 20 or 19 would suffice. If I was to pick 17 or 18 or 19 or 20. So they're all the possible tickets I could pick in the first pick. Now they all go back in. But to keep it 35 or more, 20, 19 or 18. See that? Then 20, 19, 18 or 17. 19 with 20, 19, 18, 17 or 16. And 20 with 20 or with 19 or with 18 or with 17 or 16 or 15. Now I'm labouring the point because I want to show you what the sample space looks like. So you've got those two or any one of those combinations, any one of those 3, any one of those 4, any one of those 5, and any one of those 6. Okay, so what does that mean? You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 out of the 400 combinations will give me answers of 35 or greater. Now, are E and F independent events? Well, if they are, then the probability of E multiplied by the probability of F will be equal to the probability of E intersection F. That's the great independence rule. What's P of E? P of E is 4 over 5. What's P of F? 21 over 400. Now, I want you to think about this for a moment. Is there an overlap between the two? So, pink tickets, are there any pink tickets that can give me a total of 35 or more with the green ones? Or, sorry, any green tickets that can give me 35 or more with the pink ones? Well, 20 and 15, that one there can. And then the 15, where are we? 20, this one here. So we have 1, 2, 3, 4, 5, 6. There are 7 possible combinations that will give 35 or more if we're using either of these 2 green tickets. Okay, that's the overlap. So it's to be green, and it has to be a total greater than 35 or equal to 35. So with 15, only 20 is possible. But with green ticket 20, there are 1, 2, 3, 4, 5. There are 6 possibilities. So there are 7 altogether. So that is 7 out of the 400. Okay, so let's see what happens when I multiply these. Is that a true statement? So 4 over 5 multiplied by 21 over 400. And when I multiply those, I get 21 out of 500. So are they independent? No. They should be if that was the case. What do I get when I multiply these together? I get 21 out of 500, which means no, they are not independent. So therefore, we simply report that fact no by showing the answer that's there. Okay. Now, time for you to take over, because I'm breathless now at this stage. I want you to take the questions on 81, 82 and 83 together with the questions I gave you in relation to the earlier slides, and just work your way through them. And again, if you have any problems, please feel free to email me.